A logical argument is a set of statements that are made to support another statement. Now, the parts of the logical argument are premises. Each one individually is called a premise. Those are the supporting statements that act as the evidence for the argument. And then the conclusion, which is a statement that we want to test for its truth value, and the conclusion is supported by the evidence. Here's a sort of argument that we see quite often in the world of mathematics. It's an example of something we call the transitive property, and we see it in algebra. The first two statements, if A equals B and B equals C, are each a premise of the argument. And the conclusion is then A equals C. This is an example of a valid argument. It's an argument that's true for all of the truth values for A, B, and C. On the other hand, here's an example of an argument that contains some words. So, all dogs have 4 legs is a premise. All tables have 4 legs is a second premise. Therefore, our conclusion is all dogs are tables. This is an example of an invalid argument. It's an argument that might be true under some conditions, but it isn't always true. In other words, you might have a dog that's perfectly willing to act as a table, but probably not all dogs are willing to act as tables. In that last example, you can see that logical arguments quite often have words. And what we'd like to do is take those arguments that contain words and translate them into symbols so that we can use what we know about truth tables to decide whether the arguments are valid or not. Here's an example of a logical argument with words. If I buy pasta, then I'll make you dinner. I didn't buy pasta, therefore I didn't make you dinner. There are 2 premises to this argument and a conclusion. In our first premise, we can see a simple statement, I buy pasta, and we'll assign that the letter P. We can also see a simple statement, I'll make you dinner. We'll call that Q. Now, when we look at the other premise, we can see I didn't buy pasta is just a negation of P, and in the conclusion, I didn't make you dinner is just a negation of Q. So we don't need any more variables to define our simple statements. So let's take each of the sentences and write them in terms of our variables P and Q. So in the first sentence, if I buy pasta, then I'll make you dinner, we can write if P, then Q. I didn't buy pasta is not P, and I didn't make you dinner is not Q. So we have our 3 sentences now translated into symbols, but in terms of writing this so that it looks like a logical argument, we're going to do a couple of other things. First of all, we'll put a line in between the 2 premises and the conclusion. And secondly, you'll notice that our logical argument contains the word therefore, and we'll show that with these 3 dots. Now we've got the individual sentences written in terms of symbols, but what we would really like to do is take this entire logical argument and write it as one symbolic statement. So here's what we need to think about. With every logical argument, what we're saying is that if we assert the premises, then we can come to the conclusion. In this particular logical argument, we do have 2 premises. So we could say, if I have premise 1 and premise 2, then I have the conclusion. Now let's go just a little bit further so that we can incorporate our symbolism. Premise 1 we know, that's if P then Q. Premise 2 we also know, that's not P. And the conclusion we also know, that's not Q. So what we could do is substitute those symbolic statements for the words we have. So premise 1 and premise 2 can be substituted with their symbolic equivalents. And the conclusion can also be substituted with its symbolic equivalent. Now we can do a little more substitution. You'll notice we've got a word and in there, and we have a symbol for that. And is a conjunction, so we'll use the symbol for conjunction. And we also have an if-then statement, and we know that that is a conditional statement, and we know how to represent that. We represent it with an arrow. Now we've got one line that represents our entire symbolic argument. We are going to make one more subtle change, and that is with that arrow. We do have a conditional statement. We're not changing that. But what we are going to do is replace that single arrow with a double arrow. It still means the same thing. We still have a conditional statement, but what that double arrow is signifying is that this is a logical argument. So let's take that symbolic statement for our logical argument and build a truth table for it. So let's look at the parts that make up the argument. We have if P then Q. We need a column for that. We have not P. We need a column for that. Those two are put together as a conjunction. We need a column for that. So what we have so far is our two premises that have been put together with that important connecting word and. We also have a conclusion, and we do need a column for that. And now that we've got columns for our premises and our conclusion, we need one last column for the entire symbolic argument. Now let's go ahead and complete the truth table. This is no different than completing any other truth table has been. So for the column if P then Q, we'll look back at the P and the Q column and complete that part of the truth table. For not P, we'll look back at the P column, complete that part of the truth table. The next column is a conjunction, so we'll look back at the two pieces that we're putting together with that conjunction and complete that column. Now we have a negation of Q, so we'll look back at the Q column, complete that column. And now finally, we'll look back at this column for the antecedent, that's the if part of this conditional. And we'll look at this column for the consequent, that's the then part of the conditional, to get our final column. So the whole point of doing this is to decide whether our argument is valid. Is it always true? That makes it valid. Or is it ever false? That makes it not valid. And what we notice is that last column does not contain all truths. So this is not a valid argument. And it's not a valid argument because for this condition, when P is false and Q is true, then the statements that we made to support our conclusion are not supporting the conclusion. We are basically saying a lie.